As we continue expanding our perspective of three-dimensional space, it makes sense that we should spend some time thinking about some basic shapes. One of the most basic shapes to work with is a line. In 2 dimensions, we often represented the equation of a line using slope-intercept form. If we think about graphing a line from this equation, the intercept gives us a starting position, and the slope gives us a direction. While it may seem simple, this framework turns out to be useful for thinking about lines in 3 dimensions. We'll begin by looking at the definition. Definition: a line in space is the set of terminal points of vectors emanating from a given point P that are parallel to a fixed vector V. At first, this may feel nothing like what we just did, but a picture will be helpful. Here's a point P and a vector V. We want to draw the terminal points of all vectors that emanate from P that are parallel to V. Here are some examples. We should also include vectors that are parallel but point in the opposite direction. Notice how all these points form a line and that this line is parallel to V. For this reason, V is called a direction vector. If we wanted to describe how to get to any of these points starting from the origin, we would first have to move to the point P and then move by some scalar multiple of V. And this is exactly the vector form of a line. Notice that there are multiple representations of a line. We can change the point P to any other point on the line, or we can change the length of V or have it point in the opposite direction. So the equations of lines are not unique. The vector form of a line is called that because it's written as a vector equation. If we wanted to look at the individual components of a vector, we would have a set of parametric equations for the line. Both representations carry the same information, so the only difference is in how they look. We'll start with the vector equation. We're going to write this in terms of components. The vector r of t is a function with 3 components, which we will call x of t, y of t, and z of t. Notice that each coordinate is itself a function of t, since all the coordinates are subject to change if we change the value of t. We can call the starting position vector x0, y0, z0, and the direction vector a, b, c. By plugging this in and doing some algebra, we get this equation. Remember that 2 vectors are equal when each of their corresponding components are equal, so we can turn this one vector equation into 3 equations. The collection of these equations is called the parametric equations of a line. The 3 equations come together as a package so that the whole collection represents the line and not any individual part. Notice that if we have the parametric equations of the line, we can put them back together into a vector to get a vector equation. So they really are the same thing. We're going to spend a moment to look at the general idea of parametric equations. Parametric equations are equations that are related to each other through external variables called parameters. A line is a collection of coordinates using the variables x, y, and z. The external variable for these equations is t. The idea is that this one variable controls the 3 coordinate variables. For every real number t, you get a point on the line. For example, when t equals 0, you get the point x0, y0, z0. As t increases, we move further along the line in the direction of v. As t decreases, we move along the line in the opposite direction of v. In some sense, the parameter t controls where along the line your point is located. In fact, if we vary t smoothly, we would trace out the entire line. In lots of applications, we think of t equals 0 as the starting time of some activity, so it should not be confusing to think of x0, y0, z0 as the starting point. Continuing along with the time analogy, as time increases, we can imagine ourselves walking along the line at a constant speed in the direction of v. For negative values, we simply think of that as winding time backwards and think about where we would have been had we been traveling along the line at a constant speed before t equals 0. The line itself is the set of all points that we visit along this path. When we think about the intersection of lines, we're thinking about whether the 2 paths intersect, not whether the people moving along those lines actually get to meet each other. We use 2 different parameters when talking about 2 different lines to remind us that the parameters are independent of each other. So for the first line, we may be at the intersection at t equals 1, and for the second line, we may be at the intersection at s equals 2, and we would still say that the 2 lines intersect each other. In some situations, you will need to find the equation of a line. Just remember that you need to identify a point on the line and a direction vector. The exact method you use to find those will vary from problem to problem. It can be helpful to sketch a picture sometimes to help visualize the situation. But in the end, you just need 2 pieces of information, a point on the line and a direction vector. In the next video, we're going to take a look at the next step up from lines in 3 dimensions and try to understand how to describe planes in 3 dimensions.